All right, so now let's talk about an altitude. So an altitude of a triangle is the perpendicular segment from a vertex to the opposite side, or to the line that contains the opposite side. When you think of the word altitude, you think of height. How far away is an airplane from the ground? Well, in a triangle, we use altitude the same way. We want to go from the vertex to the opposite side, and we always measure from a point to a side through a line that goes through that point that's perpendicular to the line. So much like this here, we want to know what the altitude, so how far away from the other side is the angle, is the vertex of the angle. Well, sometimes, like when we have a obtuse triangle, to get there, we have to extend out the side, out past the triangle, to be able to measure how far away from that line that point is. And that's what it says. And that's where it says to the line that contains the opposite side, because we got to extend it out, because we can't go in here anywhere and get a 90-degree angle. It's not possible, and we always measure the shortest distance, which is at the perpendicular. Well, as some of you have already guessed, the lines containing the altitudes of a triangle are concurrent. Much like the perpendicular bisectors are concurrent, at the circumcenter, the angle bisectors are concurrent. At the incenter, in a previous video, we talked about how the medians are concurrent at the centroid. Well, when we have altitudes, their point of concurrency is called the orthocenter of the triangle. And unlike the circumcenter, which is equidistant to the angles, the incenter, which is equidistant to the sides, or the centroid, which splits up the medians by 2/3, 1/3 of the length of the median, the orthocenter doesn't have a superpower other than it exists. But it does exist, and much like the circumcenter, we can find it in various places. It's going to move around. So in an acute triangle, we're going to find it inside of the triangle. If we have an obtuse triangle, we're going to find it outside the triangle, which makes sense because we have to extend the lines, the sides of the triangle out to get our altitude at all. Two of them are going to be outside of the triangle. So where are they going to meet? Outside the triangle. If we have a right triangle, it's going to be on. And in fact, it's going to be right here at the vertex of the 90-degree angle, which if you think about it, this is the distance from this side to this vertex at a 90-degree, so it is an altitude. This leg over here, this goes from the vertex to the opposite side at a 90-degree angle, so it's an altitude. So the right angle is already the place where 2 out of the 3 altitudes meet. So it has to be the place where the third one meets, because we've already drawn in 2 altitudes when we created the triangle. So let's find ourselves an orthocenter. And just like with anything else, when we have a coordinate plane and coordinate points, we're going to graph it and see what we're dealing with. So x is at -5, -1. So that's right there. Y is at -2, 4 up here. And z is at 3, -1. So we're drawing in this triangle here. And we want to find the orthocenter, so that means the point where all three of the altitudes are concurrent. Well, how are we going to do that? Well, we're going to find the equation of the altitude. Which altitude? So are we going to go from point X to YZ, from Z to YX, or from Y to XZ? Well, my preference, since XZ is a horizontal line, the line perpendicular has to be a vertical line. We're going to go from Y to line XZ. Well, it has to be a vertical line, so it's going to go along this grid line here. Y is at -2. It's a vertical line, so we're going to have x equals something, and it's going to be -2, just like in the y coordinate, which is why I picked it, because it makes it super easy. Then we're going to find the equation of a second altitude, because then we can do a system of equations to find where the two lines meet. That has to be our orthocenter. So we're going to find the equation of the altitude from, so now it doesn't matter which one we pick, although looking at them, I can tell that YZ is going to be a slope of -1. That's going to be easier, so I'm going to pick that one. But because I know that's easier, and you guys aren't going to believe me unless I show you, so we're going to go from Z to XY. We're going to pick the one that's a little more involved. And by little, I mean very little. So we got to find the slope of XY. So the slope of XY is the change in Y over the change in X. So we get 5 over 3. That's the slope of XY. So the slope of the line perpendicular to XY is the negative reciprocal, or -3/5. So let's go ahead and find the equation of our altitude, because we do have a point that it goes through, and it's right here. It's Z. So we get -1 equals -3/5 x, which is 3, plus b. And so -1 equals -3 times 3 is -9. 5 times 1 is 1, plus b. So we got to add 9/5 to both sides. So -1 is 5 over 5. So 9/5 minus 5/5 is 4/5 of my b. So my equation of my line is y equals negative 3/5 x plus 4/5 as my slope-intercept form. And then the last step we're going to do is we are going to use, let's get this stuff out of my way, move it over there. The system of equations to find the orthocenter. So I have this equation and I have this equation, so x equals -2. So it's going to be somewhere on this line, x equals -2. So I'm going to plug in my -2 into my equation. So y equals negative 3/5 -2 plus 4/5. So y equals positive 6/5 plus 4/5. So y equals 10/5 and y equals 2. So my orthocenter is at -2, 2, -2, 2. Right there's my orthocenter. And so my altitude from z to xy is right there. And go ahead and find the altitude from x to yz, plug it into the system of equations with x -2, and see if you don't get the same answer. Spoiler alert, you will. So let's do our example again with different coordinates, just to make sure we understand what we're doing. Step 1, we're going to graph triangle DEF. So we get 0, 6. We get -4, -2. And then we get 4, 6 for F. We'll draw in our triangle right here. And we can clearly see that it is an obtuse triangle, so we're going to have to expand out our lines out past the triangle to get it altitudes. Well, I see that if we find the equation of the altitude from E to DF, it's going to be x equals -4 right here. I love the ones that make it easy on me, so we're going to do that one first. And then we're going to go, I think I just want to go through D to EF. So let's find the equation of the altitude from D to segment EF. So let's find the slope of EF. So we get 6 minus a -2 over 4 minus a -4. 8 over 8 equals 1. So the slope of my line Perpendicular is going to be -1. And I've got right here point D that it goes through, so I'm going to use that to find my y-intercept, which is going to be 6. Oh, well, that was easy enough. So I get y equals -x, -1x, right? Plus 6. Then I'm going to use my system of equations to find the orthocenter. So y equals -1 times -4 plus 6. This is a 6. It looks like a B, I know, but it's actually a 6. So y equals 4 plus 6. So my orthocenter is at -4, 10, -4, 10, right there. Which is my orthocenter. It's what I'm looking for. And we've done it. And you could also do it by finding from F to the extended line ED. You're going to get the same exact thing. Let's do this, in fact, to my 2 points of line, and I can see that you can see that I have a -1 slope on that. So it is perpendicular to EF. You can see that quite clearly. All right, so let's do some more stuff and see what we can do. So is the orthocenter of the triangle with the given vertices inside, on, or outside the triangle? Well, it depends on what type of triangle it is. Let's plot it, see what kind of triangle we have. So A is 0, 3. B is 0, -2. And C is 6, -3. So we have quite clearly an obtuse triangle. So we are going to be outside of the triangle. Let's do another one and see where we land. So we go -3, -4 for J, -3, +4 for K, and then 5, 4 for L, and that is a right triangle quite clearly because we're right on the corner there. So of course it's going to be on the triangle, and it's going to be at K at -3, 4 for the orthocenter. So let's put together a quick little primer and remember all the things we have for the segments and triangles. So right here, we have a segment at a right angle that bisects it, so it is perpendicular. And it bisects it because it cuts it in half. It's a perpendicular bisector. Perpendicular bisectors are concurrent at the circumcenter. And the circumcenter, P, of a triangle is equidistant from the angles of a triangle. Perpendicular bisector, concurrent to the triangle, and that's what that diagram looks like. Here, we've got an angle bisector. And and the three angle bisectors of a triangle are concurrent at the incenter. And the incenter of a triangle is equidistant from the sides of the triangle. There's a diagram that shows an incenter. We know that I is an incenter because it is equidistant from the sides. Those are three congruent lines. Here, we're going from a vertex to the midpoint of the opposite side. Makes it a median. Medians are concurrent at the centroid. And the superpower of the centroid is it is 2/3 of the distance from the vertex to the midpoint. So it's going to cut that median into a 2/3 section and a 1/3 section. And how do we know that R is a centroid? Well, this diagram is missing a little information. That lets us know that R is a centroid. And then the last one, right angle goes to the vertex, so it is an altitude. Altitudes are concurrent at the orthocenter. And the orthocenter has no superpower other than it exists. And there's a diagram that shows us clearly with an orthocenter because we're going from the vertex to the side at the other, to the opposite side at a perpendicular line. We have three of them, so O is the orthocenter. And we are done.